Hello everyone, and welcome to Unit 2. You made it past Unit 1. So we're going to look at what it means to be continuous and the types of discontinuity, something that makes it not continuous. So what does it mean to be continuous? And if you looked at your worksheet that we had already looked at, one thing that you need to realize is that the limits have to exist. So the limit from the right and the limit from the left have to be the same. And so therefore the limit as x approaches a of f of x exists. And so that's the key part. You know that if we've got two lines not touching, it can't be continuous then, right? The next part is that it has to be defined at that value. So the limit may exist, but it also has to be defined at that value. The last thing is, if the limit exists and it's defined, those two better be equal, or else you've got a hole. So we know that the limit as x approaches a of f of x equals f of a. And so those are the three things that must happen for it to be continuous, and you're going to need to prove that to make sure it's continuous. So four different types of discontinuity here. Removable discontinuity, this comes with a hole. This is a hole. We know that it can look like, that's a rather large one, but that's okay. And what do we know about removable discontinuity? Well, the limit exists, but f of a may not be defined. And if we're worrying about that, that's a right there. Let's see, let's jump discontinuity. So we've got something here, maybe a closing circle there, and then straight out. So that's jump discontinuity. We usually see that with piecewise functions. Not always. I guess I could say usually. It's not always piecewise functions. Make sure you understand that. It's not always that. And you'll be doing examples in class where it's not piecewise functions. But here, the limit as x approaches a does not exist. This is a. Vertical asymptote in an even power. You should really have the word power there. So we talked about this in class the other day, where this is a, and so the limit as x approaches a of f of x equals infinity in this case, but f of a does not, is undefined. And the last one, vertical asymptotes that are odd power, we know can look like 1 over x. And therefore the limit as x approaches a, in this case 0, of f of x does not exist. And so those are the four types of discontinuity that we're going to be looking at. Basically asymptotes, removable discontinuity, and then jump discontinuity. So going on to page 2 here, the important facts of discontinuity. We talked about this again. 1, polynomials are always continuous. They're smooth and continuous. 2, rational functions are continuous at every number where the denominator is not 0. Again, rational functions are where two polynomials are divided by each other. 3, discontinuities occur where the denominator is 0, hence number 2. And 4, absolute values of the continuous functions are continuous. So we've got 4 examples here. This one, we should always notice here that we can factor and so therefore we notice that those two factors cancel just like we did in lesson 1, and therefore we have removable discontinuity at x equals 4. We also, make sure you realize this, yeah, we have removable discontinuity here, but we also have a vertical asymptote x equals -1. We cannot forget, wow, poor handwriting today. Cannot forget about this factor there. So we have two spots of discontinuity. One at x equals 4 that's removable, and we have a vertical asymptote at x equals -1. Let's go. With this one, we've got 3 minus x. We're going to set the denominator equal to 0. Remember, when it's absolute value, we do both the negated part and the positive part. So that implies we got x equals 3 and x equals -3. This is asymptotic discontinuity too. So please make sure you realize that. That's where the denominator equals 0. I don't know why I haven't changed these two examples. Both of these, if you notice that also equals sine x over cosine x, and this equals 1 over cosine x. So we're going to get the same answer for both of these. But we have to set the denominator equal to 0. And when we do this, we have to go on the unit circle. Where's cosine equal to 0? Well, there and there. Remember, this is the x value. So we know that x is going to equal pi over 2. It's 90, 270, 3 pi over 2. But notice that there's no domain given for either of these, and therefore we can't just stop. 5 pi over 2, 7 pi over 2, and it keeps going. So our answer to both of these is going to be that x equals k pi over 2, where k is an odd integer. Now, another way that we like to write this is x equals k pi over 2, comma, where k is an element of and this is another way of saying 2 times any integer plus 1. Well, we do 2 times any integer to give us an even number, then we add 1 to make sure it's an odd number. So either way, that's a k and that's an element symbol. Wow, should just rewrite that. There you go. So 2 times any integer, of course, is going to give you an even integer, and then we add 1 to make it an odd integer. And last but not least, we'll look at this one. 2 cosine x minus 1 is in the denominator, so we're going to set 2 cosine x minus 1 equal to 0. We get cosine x to equal 1/2. And therefore, we need to remember that cosine of 1/2 occurs at the reference angle of pi over 3, or 60 degrees. And so where is it positive? Well, when we do this, it's positive there and there. That's more like 30, not 60. So we're looking at pi over 3, comma, 5 pi over 3, comma, 7 pi over 3, comma, let's see here, 11 pi over 3. Notice that we don't see a pattern here. And so you will realize here that we keep adding this one and that one at 2 pi, because we keep going around in a circle. And with this one and that one, we added another 2 pi, because we kept going around in a circle. It's always going to be here, it's always going to be there. And so we keep going around and around and around. So the easiest way to write this is x equals pi over 3 plus 360 degrees, which is 2k pi, comma, where k is an element of any integer. and x equals 5 pi over 3 plus 2k pi, comma, k is an element of any integer. The reason why we're doing that is instead of having to try to find the pattern or just saying it's those two, the domain is not restricted here, and so therefore we have to add 360 degrees. The joke of the day: why do mathematicians like parks? Because of natural logs. That was good. Natural logs. You guys have a good day, and I'll see you in class.